Hi, this is Farhan from AlgosFromScratch, and I welcome you to this amazing YouTube playlist on building DistilBERT model from scratch using PyTorch. And in this video, we are going to start the transformer block. So let's have a recap. We, till this point, have completed these topics. We started with the embedding layer. Then we tested it with a naive classifier. Then we built the single head self-attention. Then we converted this single head attention into multi-head attention. And we then built our feed-forward network in our last video. And the next step is now we are going to develop a whole transformer block. This transformer block, if you remember this architectural diagram, here is the transformer block, that inner box. Basically, this is the transformer block. Inside this, you can see we have, first of all, this multi-head self-attention. Okay, we have implemented this. Then we have this SA layer norm, and then we have this feed forward. So we also have implemented this feed forward network, and then we again have this output layer norm. So if you look into this block, we just have this concept left to discuss. And in this video, we will start with this Add&Norm. So if you look into this step, first thing you can see that is adding some matrices, okay, and then passing it to the layer norm. So this step is called Add&Norm. So once we are done with this Add&Norm, it is repeated again, okay, here. So once we are done with the understanding of this Add&Norm, we will then quickly implement it, okay. To understand this as a layer norm plus the addition part, I will call it Add&Norm, okay. And in the original paper, it is also called Add&Norm, okay. So I've listed these points, okay, and with these points, I will explain what basically this Add&Norm layer is and what's the intuition behind this. Because I just want to give you the intuition so you have idea why we implement this Add&Norm layer in the transformer block, okay, and why is it important. So starting with what it is, so if you look into this diagram, you can see there are two paths. First of all, input comes through this multi-head attention layer, and there's another dotted line. This comes directly to this next step where we basically adds the hidden state that we passed to the transformer to the multi-head attention block as well. We just add the original input to the output of this multi-head attention block, and that is the addition part of this Add&Norm. We then pass it to the layer norm, okay. So what it is, basically, we have the output that is equal to X, the original input, and the sublayer X, we just add the output of the sublayer to the original input. Okay, so the input is added back to the sublayer's output. Now what it basically fixes, this is very interesting part, it fixes the vanishing gradients that is very possible in deep neural networks. Okay, so transformers are, we kind of stack multiple blocks, transformer blocks. In this architecture we are having 6 transformer blocks, a stack of 6 transformer blocks, but there could be maybe 100, okay, for very large models. So this residual connection basically helps us in resolving the vanishing gradient problem that we can face in deep neural networks. How? So the output, basically, let's say the output is y, it is equal to x plus sub layer of x. Okay, so if you take the gradients, we can say that d of y d of x will be equal to this plus the sublayer part. Okay, so this always gives us 1, and this part can be near to 0. If let's say it is near to 0, still the gradient will have something like 1 plus something. Okay, so it will never come near to 0. Okay, so with this, now we always have a strong signal that we can send to the early layers, like the previous layers, and the previous layers also get strong learning signals. Okay, and in this way the previous layers never get vanished. Otherwise, if we do not add this residual connection, this network can have, let's say this sublayer can have the this sublayer, specifically this output, can be near to 0, and when it is near to 0, then this is what the vanishing gradient mean. Okay, so we will not have very strong signals to send to the previous layers. So this gives us a shortcut, okay, to send the strong signals to the early layers, and in this way it resolves the vanishing gradient issue. Okay, then of course it never learns from scratch. Okay, so we have the input, we pass this input to the layer, maybe the multi-head attention layer. Okay, and we get some output. We take this input and we add it to the output. Okay, so let's say the original input was something like A, B, C. Okay, and we through this multi-head attention sublayer, the model learned maybe this output is 1, 2, 3. Okay, so after adding, we can say A plus 1, B plus 2, C plus 3. So this delta part, this changed part, is basically added to the original input. So it only learns new features or new relationships, and we add it to the original inputs. Okay, so it never learns everything from scratch. And also this residual connection in the architecture gives us the safety net. Okay, how it basically is starts with the storing of the raw signals. So we always have these original signals accessible. Okay, and let's say what worse scenario could be in this architecture if, let's say, this multi-head attention layer, it does not perform well. Okay, and it gives this change near to 0. Okay, so what does it mean by this maths? That the worst thing can happen is in this architecture is, we can say, this layer never existed. Okay, so it just did not perform well. Nothing or no impact on the next layers. Okay, otherwise this no learning and or you can say something bad basically learned in this multi-head attention layer, maybe some noise, so it would directly be passed to the next layers. Okay, so it kind of acts as a safety net for the architecture. Okay, so this is the intuition, and now we have the understanding and we have this big picture in our mind. We know why these residual connections are in the network. Now we will just switch to the coding screen and we will implement this in our code. Okay, so this is the same notebook. In our previous video we implemented this feed forward network. Okay, now we are going to just start this transformer block. Okay, we will add the multi-head attention, the feed forward network, plus these add and norm layers. They basically are repeated twice. Okay, so I will start with, okay, so first let me just execute these, maybe we need them later on. Okay, so yeah, I will just copy this. I don't think we need this because we are not going to build anything. Okay, we are just now organizing them. So I'll just quickly run these classes and the blocks where we tested them, so just to make sure everything is fine. Okay, and yeah, multi-head attention. Okay, and we tested it working fine. Okay, yep, feed forward network, this also working fine. Yeah, so now let's just start our transformer block. So I will start with the model. Okay, so this is our model. Okay, and in this model, if I just copy the cell output and paste it over here, so this is the part that we are going to develop in this video. Okay, so you can see it is a transformer block and it has, first of all, this multi-head attention, this DistilBERT self attention, then it has the self attention layer now, then feed forward network, and then this one. Okay, so it starts from here and ends at this. Okay, so I will just copy this and let's just have this part. Okay, and I'll just clear the selected. Okay, now I will just also import something. Let me just look into the the source code a bit. Okay, so I will also show you what steps we are going to perform, okay, and what basically the real model has implemented. So I can say something like print model, and I'll just get the class, and on this module, okay, this is what I want. Okay, I just copy this, and here I'll just say something like from this I want this class, so it is transformer block class, this. Okay, and yeah, I think it's done. Now I'll just import the inspect from Python, and from this I will just print this source code. Okay, so print inspect dot get source transformer block forward. Let me print the complete class. Okay, inspect dot get source. Okay, so yeah, now you can see we have this init class. Okay, in this init we have this init method, and in this init method we have the attention layer, this as a layer norm, the feed forward, and the output layer norm. And in the forward method we get the hidden state. It's nothing but the output of the embedding layers. And attention mask, yeah, important for multi-head attention class. Okay, we have two steps in it. First one is self attention part. We just get the output from the multi-head attention class, we pass it to the layer norm, where we just add the attention output to the hidden state. That hidden state, you can see we passed it to the multi-head attention class, so output is added to the input, and then we use this output, pass it to the feed forward network, and whatever the output is we store it in this FFN output, and then adding it again to the whatever we passed to this layer. Okay, so whatever the output is, then at the end we simply just return the output. Okay, so starting with the class. Okay, and I'll just have the same name with one. Okay, my. Okay, so this, and then my. Okay, I'll start with inheriting it from the nn.module. Okay, and here first let me start with, okay, so let me look into this suggestion self. Okay, first of course we need the dimension. Okay, okay, so first we will start with the constructor. Okay, and let me accept these suggestions and look into this. Okay, so dimension, number of heads, okay, for multi-head attention, hidden size, we can get it from this. Okay, and then the dropout, we have this from the configuration file. Okay, I'll just remove all of these. If I need anything, I have the model config dictionary, I will just take them. Okay, Now here, first of all, I will just create the self dot attention. Okay, so the first, let me just clear this output. Okay, and the first one is this attention. Okay, so I will just create the self dot attention. It is going to be equal to multi-head attention. We are already passing all the config to the multi-head attention class, so we'll just simply call it like this. And then the next thing is SA layer norm. Okay, so here you can see the next argument is SA layer norm. I'll just simply copy this and create a layer norm. Okay, so self dot layer norm and then layer norm model config dimension. Yep, fine. Now I hope you understand this. Okay, I've explained them already, so I'll just quickly accept these suggestions. Feed forward network is feed forward my. Yep. And okay, so this one I need to check multi-head attention if the name is correct. Yep, this is the name. So I'll just copy this and paste it over here to avoid any kind of issues. Okay, so this over here, I think it's fine. Now the next is our forward method. Okay, this forward method will take first of all the self. And okay, now what we are going to do in this forward method, you can see here in the code. Okay, so I just cleared the code. Okay, so we are basically calling the multi-head attention. So in the multi-head attention, if you remember, we are passing the input embeddings plus the attention mask, and it gives us the output. Okay, so the multi-head I will just take the input embeddings, okay, plus the attention mask. Okay, and that is all. Okay, I will start with first of all the attention part. Okay, in the attention part I will get the multi-head attention output, so let me call it multi-head attention output. It is going to be equal to self dot attention, and inside this I will pass the input embeddings, okay, plus the attention mask. Yeah, done. Okay, now I'll just modify this output with the addition of input and the output and passing it to the layer norm. Okay, so this suggestion seems right. Input embeddings, whatever we pass to this. Okay, let me just have this MHA output equal to self dot SA layer norm. Okay, I'll accept it. Let me just remove this part for now. Okay, so input plus the MHA output, we get our this part done. Okay, so if I show you here, we passed our input to this multi-head attention, and whatever output we get from this, we applied this part on the output. Okay, so this hidden state, basically the input embeddings plus the attention output, and we are applying this layer norm. Okay, so add and norm. Okay, then now the next part is we are going to implement the feed forward network part. Okay, here what I will do, I'll just say feed forward network output. Okay, that is equal to simply just this feed forward network. Okay, and I'll pass the output of the previous layer. Okay, so self dot ffn, and here I'll just pass this output to the feed forward. Okay, and I'll get some output. Okay, again, if you remember, in this architecture we implement the same add and norm. Okay, with this I'll just call the ffn out, and it will now be equal to the self dot output layer norm, and let me remove this for now, where I will be just adding the multi-head attention output. Yes, whatever we pass to this feed forward network, we add that input to the output of the feed forward network. Okay, so this is done. I'll just quickly check. It is good practice to test it. Okay, so before moving on, I will just get the MHA output. Okay, and now I will just copy something from the previous code from this part. Okay, I'll just copy this and I'll test my code over here. Okay, so let me paste it over here. So you can see now we are basically having this input to the tokenizer. We are getting input IDs plus attention mask, and we are then passing it to the embedding layer. Okay, and whatever embeddings we get, we are passing it to the multi-head attention. So at this point now we need to have the transformer block, the transformer block object. Okay, and this transformer block object is equal to this transformer block. Okay, so here I'll just replace it. So this is the object of transformer block now. So this MHA output will literally be the MHA output. Okay, so I'm just printing the MHA output. Okay, I'll just remove it because everything is now done within this transformer block, so no need to call the feed forward network separately. Now this is done. I'll just, okay, my bad, this one first and this one again. Okay, so see, we just passed this input embeddings to the transformer object. Okay, no, we are passing these. Okay, so let's just test it. Oh, okay, so we are getting the multi-head attention output. Okay, now I will just remove this from here. I'll let the output of the multi-head attention pass through this feed forward network. Okay, and whatever the FFN out is, I'll just return it. Okay, you can see the same. Okay, so this is pretty much it for this feed this transformer block. So this is now a transformer block. Okay, so this complete transformer block with these 4 steps, if you just notice this, we are having first of all this attention output. Here we are applying the add and norm here. Then on the feed forward part we are passing the output of the multi-head attention to the feed forward, and whatever we get as an output from the feed forward, we are passing it to the layer norm with this Add&Norm process. Okay, and we get our output. Okay, now quickly just execute this and see if anything else is remaining. So you can see, first of all, the attention output, then this layer norm with addition, then this feed forward and output layer norm. Okay, so pretty much it for this one, I think. Yeah, done. So yeah, that is all for this video. I hope you enjoyed the video, and I see you in the next video. Till then, bye bye.